this k here, I choose either A or B, and I let I run from A to B. Okay, we've done this in class. And so that's what I'm going to do. Right, so the first is I'm going to write it for the situation when k equals A. When k equals A, and I runs from A to B, that means that I can be either A or B. So the first possibility is A. Okay, and then I have HAA minus E, I is A, this is the same, I shouldn't write that, S AA. That's the first one, the first possibility. The second possibility is when I equals B, so I get CB, and then HBA minus ESBA. That should be 0. That's the first equation. Is there a second equation? Yes, there is, because in all of this, in this whole line here, this was K, which is A. I'm going to repeat the same thing, but now for the K equals B. That's the second equation. So that looks like this. Okay, so these are the two equations. There's a couple of things I can do. I can replace all these HAAs by alpha, because that's an alpha. This is alpha. Okay, and HAB is beta, so that's good. That's beta. SAA is 1. That's good. That's just 1. And this one is beta again. This one is alpha. Beta, alpha. And this one is 1. Okay? And also I say, of course, SAB is same as SBA. So I can just eliminate that. So these are the equations that I have in terms of alpha, beta, and S. Now, if I would apply what I know about this problem, because I know that Ca and Cb for the bonding orbital are both 1. Okay? They're both 1. And if you do that, you can see that these two equations are basically the same. Okay? So if Ca and Cb are 1, then the equation that I'm having is actually very simple. Let's write it over here. I simply get alpha minus E plus beta minus ES equals 0. If I rewrite that in terms of E, I see this, which means that E equals alpha plus beta, 1 plus S. This is the energy of the bonding orbital. This is the energy of the bonding orbital. Can I do the same thing for the anti-bonding orbital? Yes, you can. Now C equals 1 and CB equals negative 1. Okay, and if you do the same analogy, same thing, what you find is that E minus equals alpha minus beta, 1 minus S. So, using the secular equations from the variational principle, I can write out the energies and the wave functions for this problem. Okay, question C. Now I have some values for alpha and beta and for S, and I have to determine the energies, okay, into an orbital level diagram. So let's do that. The orbital level diagram looks like this, where this is alpha, which has the value negative 5.00 electron volts. Doesn't matter what unit it is in, because it's, you know, just a unit. Electron volt is an energy unit, just like joules. I have expressions for the energy of the excited, or not the excited state, of the bonding orbital, as well as for the anti-bonding orbital, which is over here. And I have values for alpha, beta, and S. I'm just going to simply pop them in to these equations and calculate what these energies are. So E negative with these values is 4.44 electron volts, and E plus equals negative 5.45 electron volts, which is good. This complies with my general notion. I have alpha, which sits at minus 5 electron volts. Alpha plus sits below it, it's more negative. The E minus, which is the anti-bonding orbital energy, sits above it. It is less negative. Final question of problem 9. If S becomes larger, does the energy splitting between these two orbitals increase or decrease?
Decrease.
Decrease. I hear it. Let's have a look. If this one becomes larger, that means that the denominator is going to be smaller. That means that the splitting, at least for the molecular orbital anti-bonding version, is going up. Oops, sorry. Yes. If this is going to be smaller, then this distance is going to be larger, right?
What it's asking if it's
Huh?
no. As this becomes larger.
If here, however, you see if
I
S becomes larger, this whole thing becomes bigger. That means that the energy here becomes smaller. So this one is going to creep up. This one is going to creep up as well. But this one creeps up quicker than this one, so overall it becomes smaller. It turns out if you change S, if you make it too large, you get unphysical results. Okay? And this is one of the kind of like consequences, if you wish, from us making the assumption that the previous assumptions we made in order to get to these answers. These approximations will not bite us in the bum. And we end up with unphysical results if you keep increasing S. So S in this whole formalism needs to be somewhat small, much smaller than 1. 0.1 is small, 0.9 not so small. Too close to 1, and you'll see you get unphysical results. Yes?
If the splitting between the MOs decreases as this becomes larger, then eventually won't they just be like really similar to like very close to the energy level basically? So would that be the like unphysical result you're talking about?
Yeah, but you can the unphysical result is that these things can actually, this one can go actually over this line, and it becomes unphysical.
Yeah.
Okay, so I don't think I have time to go over problem 10. But